Welcome back to the deep dive. Today, we're plunging headfirst into a topic it's really reshaping the landscape of artificial intelligence, particularly in the realm of advanced coding and these new agentic models. Imagine, just for a moment, having an AI that doesn't just, spit out a few lines of code, but actually deeply thinks through complex software engineering problems. Strategizing and adapting, much like, like a seasoned human developer, that's the really exciting frontier we're exploring today. So our mission today is to take a comprehensive deep dive into the Qwen3 series of large language models. We're going to put a special focus on their most agentic code model yet, Qwen3-Coder. We'll be extracting the most important technical nuggets and maybe some surprising insights from their recent blog post, Qwen3-Coder, agentic coding in the world, and also that really detailed Qwen3 technical report from ARC6. And as always, our commitment to you, the curious listener, is to focus purely on the technical details and their profound implications for the field. We'll be steering clear of any ethical considerations or, inclusivity discussions to keep our exploration tightly focused on the groundbreaking innovation itself. Oh, and for those of you who want to stay updated on the latest AI and ML research papers, remember to visit our webpage. The link's right there in our bio.
Yeah, and what's truly fascinating in here, I think, is how these new models are just pushing the boundaries of what we thought was possible, especially in automated software development and complex reasoning. If we connect this to the bigger picture, it's really about dissecting how these core technical capabilities, things like, vastly increased context length, these hyper-efficient architectural designs, and incredibly sophisticated training paradigms, how they translate directly into tangible state-of-the-art performance gains. You're going to gain a rapid, yet I hope thorough understanding of not just what these advanced systems can do, but crucially how they're built and what exactly makes them perform at such an exceptional level.
Couldn't agree more. And when we talk about agentic coding, we really are talking about moving beyond just like simple script generation or filling in a single function. It's about an AI system that can operate almost autonomously within a complex software environment. And leading this charge is their flagship model, the Qwen3-Coder 480B A35B Instruct. Now, okay, that name is a bit of a mouthful, isn't it? But the core insight here lies in its architecture. It's a mixture of experts model and MoE model. What this means in practice, essentially, is that while the model boasts this staggering 480 billion total parameters, only a small fraction, just 35 billion, are actually active at any given time for a specific task. And this is where the real efficiency kicks in.
Exactly. And that efficiency isn't just like a minor tweak. It's a really profound shift.
Right.
It lets you harness the immense knowledge and problem-solving power of truly massive model, but you get the agility and significantly lower computational costs during inference, almost like running a much, much smaller model. This really redefines that traditional trade-off we always see between model size and deployability. But beyond just the parameter count, the next major leap comes in its context length. Qwen3-Coder natively supports an astounding 256,000 tokens. And through these advanced extrapolation methods like Yarn, they can push it even further, up to an almost unbelievable 1 million tokens.
1 million tokens. That's a scale that's genuinely hard to wrap your head around. We're talking about an AI being able to ingest and understand the equivalent of an entire large book, or maybe even a small library, all in a single pass. But what does this kind of massive context length actually mean for coding specifically, beyond just more information? How does it fundamentally change what an AI can actually do with code?
Oh, for coding, this is absolutely transformative. It enables what the researchers are calling repo-scale processing. Think about how a really skilled human software engineer tackles a new project or maybe a complex bug. They don't just look at one file, right? They need to understand the entire code base, the architecture, the dependencies, the pull request, how different modules interact. Traditionally, LLMs they've struggled immensely with this. They only ever see a limited window of code at a time. Makes it really hard for them to grasp the holistic context of a large software system. With 1 million tokens, Qwen3-Coder can essentially read and comprehend an entire code repository, or process these massive dynamic things like large pull requests that span across countless files and involve really intricate interdependencies. This capability is absolutely fundamental for true agentic coding, where the AI isn't just generating isolated functions, it's understanding the system as a whole and making intelligent, interconnected decisions that are truly context-aware.
Yeah, that analogy of a human engineer grasping an entire code base really drives it home. It feels like it shifts the paradigm from just simple code generation to genuinely assisting with these profoundly complex software engineering tasks. Imagine your own coding projects, large or small. How much more efficient, how much more integrated could your workflow be if an AI could truly understand your entire code base at once? And it's not just a theoretical capability either, is it? This model is already setting new state-of-the-art benchmarks. Qwen3-Coder 480B A35B Instruct, their flagship, is outperforming other open source models in these crucial categories like agentic coding, agentic browser use, and agentic tool use. The technical report even highlights that it reaches parity with models like Claude Sonnet 4, which, for an open source model, that's a pretty significant marker of competitive achievement against a well-known proprietary system.
It is indeed. This isn't just about raw size. It clearly indicates that their architectural and training innovations are translating directly into competitive real-world performance. But to really appreciate this, let's kind of pull back the curtain a bit and delve into how they achieve this level of performance, starting with the pre-training advancements. A primary factor is just the sheer scale of the data. Qwen3-Coder was trained on a mind-boggling 7.5 trillion tokens. But what's particularly noteworthy, and a key insight into its coding prowess, is the incredibly high code ratio within that dataset.
Right.
And astonishing 70% of those tokens were dedicated specifically to code.
Wow, 70%. That is an exceptionally high code ratio, far beyond what we typically see in most general-purpose LLMs, which often, try to balance code with natural language, scientific texts, and lots more. Why is this specific balance, or rather this heavy skew toward code, so critically important for a coding agent? And how do they make sure it doesn't then sort of lose its ability to understand general concepts or mathematics, which are also vital for real-world programming?
Right, that 70% code ratio is absolutely critical because it fundamentally supercharges the model's deep understanding and generation capabilities specifically for programming languages. It allows the model to learn the intricate patterns, the subtle nuances of syntax, the logical flow, and the best practices inherent in just vast amounts of code at an unprecedented scale. This deep immersion into code enables a level of proficiency that, well, general models just can't achieve. The clever part, as you hinted, is that they emphasize it retains its general and mathematical abilities despite this specialization. And that balance is crucial for a real-world coding agent, because software engineering isn't just about writing isolated lines of code, is it? It involves interpreting natural language requirements, performing complex mathematical calculations for algorithms, understanding scientific principles, and leveraging general-world knowledge to interpret and solve complex problems. So it's about achieving profound code expertise without sacrificing the broad intelligence needed for real-world application. It's kind of a specialized generalist, if you will.
A specialized generalist, I like that. Fascinating. And on the context length side, beyond just being able to handle this huge volume of tokens, the technical report really digs into the ingenious engineering behind how they actually scaled it. They reiterate the native 256K context and the use of Yarn for that 1M token extension. Could you maybe walk us through some of the deeper, perhaps less obvious technical techniques they employ to achieve this impressive feat of long context understanding?
Certainly. Yeah, the report highlights several specific techniques that are definitely worth noting for their ingenuity. Firstly, they significantly increase the base frequency of rotary positional embeddings, or ROPE. They push it from 10,000 up to an astounding 1 million using a technique called ABF, absolute base frequency scaling. So to put it simply, ROPE is a form of positional encoding. It helps the model understand the order and relative position of words in a sequence, which is obviously crucial for long-range dependencies. By dramatically increasing its base frequency, they essentially stretch its ability to discern positions over much, much longer sequences, allows for more effective extrapolation. Secondly, and maybe even more impressively, they introduced Yarn, which stands for yet another rope in factor and a novel technique they call dual chunk attention, or DCA. Now, while Yarn is about optimizing rope for these extremely long sequences, DCA is a particularly clever architectural modification to the attention mechanism itself. Instead of the model having to compute attention over every single token in a 1 million token sequence all at once, which would be computationally just prohibitive, DCA helps it focus on and intelligently connect relevant chunks of information simultaneously. Think of it like a hyper-efficient librarian who knows exactly which sections of a vast library to cross-reference instantly. Makes long context processing far more efficient and manageable. These innovations combined specifically allow for that remarkable four-fold increase in sequence length capacity during inference.
That's a truly elegant solution, isn't it, to a massive computational challenge. It's one thing to hear about the theoretical capabilities, but another entirely to understand the underlying engineering. However, what often gets left out of these academic reports are the practical considerations. While they clearly outline the benefits of this immense context length, what about the computational overheads? The actual cost of running a model at 1 million token context for users outside of, say, Alibaba Cloud's highly optimized infrastructure. is the inference cost for a developer, or maybe a smaller company, linear with context length? Or are there underlying optimizations that make it more manageable in real-world deployment scenarios? That's something the papers don't always spell out.
That is a profoundly important and, yeah, rarely discussed practical challenge. While techniques like DCA and Yarn aim to make long context inference more efficient than just a naive linear scaling, they don't fundamentally eliminate the increase in computation as context grows. Attention mechanisms, at their core, can have quadratic complexity relative to sequence length. So while these optimizations might kind of bend that curve, the inference costs do increase, and often quite significantly, with context length. For users outside of a major cloud provider's highly specialized and custom-built infrastructure, managing that trade-off between maximizing context use and keeping inference costs viable will absolutely be a practical consideration. It means that while the capability is there, the affordability for widespread ad hoc use at 1 million tokens by smaller entities is still a significant hurdle. And yeah, that isn't always fully transparent in the research papers. It's a really key detail for real-world deployment.
That's a crucial insight, yeah. Something developers absolutely need to keep in mind. Beyond scaling tokens and context, they also put significant effort into scaling synthetic data. The process involved leveraging their existing Qwen 2.5-Coder model to clean and rewrite noisy data, which, according to the report, significantly improved overall data quality for this next generation.
Right, and this represents a critical and increasingly common feedback loop in advanced AI training. It illustrates an iterative improvement process. They're essentially using an existing, already capable model to generate higher quality training data for the next generation of models. This approach is just far more efficient and scalable than relying solely on human-curated data, which is both expensive and incredibly time-consuming to scale to, trillions of tokens. By having the AI effectively improve its own training diet, they can continuously refine the model's capabilities in a self-reinforcing virtuous cycle. Leads to more performant and robust systems down the line.
So it's almost like the models are helping to make themselves smarter, feeding on their own improved output. Interesting. After the foundational pre-training, the focus shifts to post-training innovations, specifically tailored for code and these agentic tasks. They discuss scaling code RL, reinforcement learning, using a paradigm they call hard to solve, easy to verify. What does this actually mean in the context of coding? And why is this particular approach so well suited for code tasks compared to, say, natural language generation where things are more subjective?
Yeah, this hard to solve, easy to verify paradigm is perfectly suited for code because, unlike more subjective tasks where human preferences or nuanced evaluations are often needed, code correctness is, well, it's objectively verifiable. If a model generates a piece of code, you can simply run it through a compiler and a suite of test cases to see if it produces the correct output or behaves as expected. This provides an immediate, clear, and unambiguous feedback signal for the reinforcement learning algorithm. It's hard to solve because writing complex, correct, efficient code is inherently difficult, but it's easy to verify because the outcome of code execution is pretty binary. It either works as intended or it doesn't. The subjective feedback enables large-scale automated reinforcement learning, allows the model to learn from a vast number of problem solution attempts and execution results, rapidly improving its coding proficiency.
That makes perfect sense. So it's really about generating diverse, high-quality test cases automatically, which then powerfully fuels the RL process for code. They also scaled long-horizon RL, or agent RL. This is designed to address those multi-turn interactions inherent in real-world software engineering tasks, like the ones you find in challenging benchmarks like SWE Bench. The technical detail that truly jumped out at me here was their ingenious solution to environment scaling. They built a system capable of running 20,000 independent environments in parallel on Alibaba Cloud's infrastructure. What's the significance of that massive parallelism for training agentic models on these complex, multi-step tasks?
Oh, that level of parallelism is incredibly significant, maybe even revolutionary for training truly agentic models. Real-world software engineering tasks are almost never single-step problems, are they? An autonomous agent needs to perform a whole series of actions: plan, write code, use various tools like compilers or debuggers, get feedback from the environment, whether it's an error message, a test failure, or a successful compilation, and then adapt its strategy over many, many steps. This long horizon interaction requires just immense amounts of data and feedback to learn effectively. Running 20,000 environments in parallel allows them to gather that crucial feedback at an unprecedented scale and speed, dramatically accelerating the reinforcement learning process. This is precisely what's needed for training agents that can robustly navigate the inherent complexities and iterative nature of real software development. And as a direct result, Qwen3-Coder achieves state-of-the-art performance among open-source models on Bench verified, even without test-time scaling, which is a powerful indicator of its inherent and deeply learned agentic capabilities.
That's a really clear marker of truly groundbreaking progress. Now, let's maybe broaden our scoop a bit and look at the entire Qwen3 series, because Qwen3-Coder is actually just one, albeit prominent, member of a much larger and more ambitious family of models. They've taken this dual architecture approach, encompassing both dense models ranging from 0.6 billion up to 32 billion parameters, and then their cutting-edge mixture of expert, or MOME, models. Specifically, the Qwen330b A3b and the much larger Qwen3-235b A22b. For their overall flagship model, the Qwen3-235b A22b, it boasts that staggering 235 billion total parameters, but here's that key efficiency insight again. Only 22 billion are actually activated per token during inference.
And what's truly fascinating here is how the MOE architecture really delivers on its promise of high performance without that proportional increase in inference cost. By only activating a select subset of parameters for any given query, it means the model can be incredibly vast in terms of its total knowledge and learned capabilities, yet remain nimble and computationally efficient for individual interactions. It's a really clever and increasingly vital way to balance immense capacity with practical deployability, making these complex models more accessible and, frankly, affordable to run.
Right. And for the dense models, they've largely retained many of the robust architectural components from previous Qwen versions, things like grouped query attention, GQA, switch CLU, rotary positional embeddings, rope E, and RMS norm with prenormalization. These are pretty well-established building blocks now. However, they also introduce some new innovations, like the careful removal of QKV bias and the strategic introduction of QK norm to the attention mechanism. Now, this might sound like a really subtle technical tweak to an outsider, but in the world of large-scale model training, what's the profound significance of these changes for stable training and overall performance?
You're absolutely right. These might seem subtle, but they're profoundly important technical tweaks, especially when you're training models at this kind of unprecedented scale. Training large language models can be notoriously unstable, they're prone to divergence, or their performance might just plateau prematurely. The attention mechanism is the very core of how transformer models process and relate information, and any instability within it can ripple throughout the entire neural network. The removal of QKV bias and the addition of QK norm specifically aim to stabilize the attention mechanism itself. By enhancing this stability, they ensure that the training process is much more reliable, less prone to crashes or numerical issues, leading to better convergence, and ultimately a more performant and robust model. It essentially means they can push the boundaries of model scale and complexity without the entire training process falling apart, which is a significant engineering feat in itself.
So it's all about building a rock-solid foundation for these immense models. Makes sense. And for the MALI models, they specified an impressive 128 total experts with 8 activated per token. They also made a deliberate choice to exclude shared experts, which is different from their Qwen 2.5 MOE predecessor, and they adopted a global batch load balancing loss. Now, this particular technical detail raises an important question for me. How does this load balancing loss technically encourage expert specialization? It implies some kind of sophisticated mechanism to ensure each expert learns truly distinct, useful skills rather than just overlapping in redundant ways.
That's precisely the aim, yeah. And it's a clever piece of algorithmic design. Without load balancing, some experts within an MOE model might become lazy or redundant, They might consistently get chosen for the easier, more common tasks, while other experts remain underutilized. The global batch load balancing loss introduces a penalty during training if the usage of experts is uneven across a batch of data. This penalty actively encourages the router, that's the part of the model that decides which experts to activate, to distribute the workload more evenly across all 128 experts. By forcing each expert to see and contribute to a more diverse set of data samples and problems, it inherently incentivizes them to specialize in distinct features, patterns, or aspects of the input data. This active encouragement prevents them from converging on similar, redundant skills and ensures that the overall model benefits from a richer, more diverse set of learned capability from its specialized components. It basically ensures every expert pulls its weight and contributes unique knowledge.
That's an excellent explanation of how they foster true expertise and efficiency within that MOE framework. Okay, now let's shift our focus to the pre-training itself, specifically the vast scale of the data and the meticulous stages involved. We're talking about a truly massive scale here. 36 trillion tokens across an incredible 119 languages and dialects. That's a huge jump, almost 4 times the 29 languages supported in Qwen 2.5. What's the profound implication of incorporating such a vast and diverse multilingual data set?
Well, the implication is pretty clear and far-reaching. This commitment to a truly massive multilingual dataset supports global deployment and cross-lingual understanding on an unprecedented scale.
Mm.
In our increasingly interconnected world, an AI model that can fluently understand and generate content in nearly 120 languages immediately possesses a much broader applicability. It facilitates more inclusive AI solutions, enabling users from a vast array of linguistic backgrounds to interact with the model seamlessly in their native tongue. Dramatically enhances its utility across various international markets, research applications, and diverse user bases. It's a very deliberate step towards truly globalizing AI capabilities.
Definitely. And it's not just about the sheer volume of data, but also the sophistication of their data curation and synthesis process. They leverage their own Qwen 2.5 VL model for text recognition from complex PDF-like documents, which is then further refined by Qwen 2.5 itself. Additionally, they generated a substantial amount of synthetic data using specialized domain-specific models like Qwen 2.5 Math for mathematical problems and Qwen 2.5 Coder for code-related tasks.
Right, this really showcases a sophisticated, multi-layered, and highly efficient data pipeline. It starts with extracting and processing real-world, often messy data from diverse sources like PDFs. Then applies a refinement step using existing capable models to clean and improve that data. Then, to scale training even further and target specific areas of knowledge, they employ model-generated synthetic data. This is a powerful strategy. It allows them to create an almost infinite supply of high-quality, relevant data for specific domains like mathematics or coding, effectively scaling training far beyond what purely human-curated datasets could ever achieve. It's a blend of real-world complexity and targeted synthetic precision.
It sounds like a highly advanced and well-orchestrated approach to data preparation. This massive and diverse dataset then went through a rigorous, almost strategic 3-stage pre-training process. Stage 1, which they call the general stage, involved training on over 30 trillion tokens with a 4096 context length, covering all 119 languages. This stage was clearly focused on instilling foundational language proficiency and broad general world knowledge.
Correct. Yeah, this initial stage serves as the absolute bedrock. It's about establishing a comprehensive linguistic foundation and a vast repository of general knowledge for the model. This broad exposure is what allows the model to understand common sense, general factual information, and the nuances of human language before it starts specializing.
Then came stage 2, the reasoning stage. Here, they shifted focus to about 5 trillion higher quality tokens. They specifically increased the proportion of specialized data, STEM content, coding examples, abstract reasoning problems, more synthetic data. The context length remained at 4096 tokens, but the explicit goal was enhanced reasoning ability. Interestingly, they even accelerated the learning rate decay during this stage, suggesting a kind of rapid push for specific skills.
Exactly. This multi-stage approach is really a technical blueprint for building advanced capabilities incrementally. After establishing that broad general foundation in Stage 1, Stage 2 specifically targets analytical and logical reasoning. The infusion of higher quality domain-specific data from areas like science, technology, engineering, and math, coupled with that accelerated learning rate decay, is designed to rapidly enhance the model's ability to tackle complex problems that require more than just language fluency. They need deep understanding, problem-solving skills, the ability to follow intricate logical steps. It's about quickly sharpening the model's intellectual tools, essentially.
And finally, stage 3, the long context stage. Here, they used hundreds of billions of tokens and significantly pushed the context length all the way to 32,768 tokens. And they incorporated those advanced techniques we discussed earlier, like the ropey base frequency increase, ABF, and the use of yarn and dual chunk attention, DCA.
Right. This final stage is where they specifically specialize the model in memory and recall over extremely fast inputs. By combining the general knowledge from Stage 1 and the reasoning capabilities from Stage 2 with the ability to handle long contexts, they create a truly versatile and powerful system. This multi-stage approach is a sophisticated technical blueprint for building advanced models, incrementally layering capabilities, broad knowledge, then specialized reasoning, and finally, that crucial ability to manage and comprehend extremely long inputs. Each stage builds upon the last, allowing for a structured and efficient way to imbue the model with a diverse set of high-level abilities.
They also mentioned developing scaling laws for optimal hyperparameters, things like the learning rate scheduler and batch size based on extensive experiments. This sounds incredibly rigorous, but what often gets left out of these research papers is the immense, almost staggering amount of computational resource and just raw experimentation that goes into finding these optimal scaling laws. It's often mentioned as systematically study the relationship, but the technical challenges and sheer infrastructure required for such large-scale hyperparameter tuning must be truly immense, almost a deep dive in itself, wouldn't you say?
Oh, absolutely. You've highlighted a critical hidden cost and effort in large-scale AI development. Discovering optimal scaling laws for models of this magnitude is anything but trivial. It's a monumental undertaking. It requires running literally countless experiments, systematically varying architectures, data sets, a myriad of hyperparameters, often consuming millions of GPU hours. This isn't just about tweaking a few settings. It's about rigorously probing the performance landscape of incredibly complex systems to understand how they behave at scale. The technical challenges involve not only the raw compute power, but also sophisticated experiment management systems, advanced data analysis to interpret results, and predictive modeling to extrapolate optimal settings for even larger future training runs. It represents an enormous, often unstated investment in infrastructure, engineering talent, and sheer persistence, which often gets condensed into a single, seemingly simple sentence in a research paper.
That's a truly insightful glimpse into the engineering effort behind the scenes. Okay, moving on to post-training. This phase is all about unlocking the truly advanced capabilities we've been discussing. They highlight two core objectives. Firstly, thinking control, which involves integrating non-thinking and thinking modes with a customizable thinking budget. And secondly, strong to weak distillation, a technique for optimizing smaller models. Let's start with thinking control. Their flagship models follow this meticulous four-stage post-training pipeline. The first stage is what they call long-caught cold start. This aims to instill foundational reasoning patterns using a carefully curated dataset of math, code, logical reasoning, and STEM problems. They apply rigorous query and response filtering to ensure only genuinely complex problems requiring chain-of-thought reasoning are included.
Yeah, this cold start phase is crucial because it's kind of like giving a student the fundamental systematic steps of problem solving before you expose them to highly complex, open-ended challenges. By rigorously filtering the data, they ensure the model isn't just learning superficial patterns or memorizing answers. Instead, it's forced to engage in genuine, step-by-step reasoning processes. The cold start also aims to use a minimal number of training samples and steps initially. This helps prevent over-optimization too early, which preserves flexibility and adaptability for the later, more advanced reinforcement learning stages. It's about establishing a robust, innate reasoning ability right from the ground up.
Okay. Then stage 2 is reasoning RL reinforcement learning. Here, they use query verifier pairs that are not present in the cold start set. These pairs are learnable, challenging, and cover broad subdomains. They employ GRPO generalized policy optimization with large batch sizes, high rollouts, and off-policy training for sample efficiency. They even went as far as addressing balancing exploration and exploitation by carefully controlling model entropy. The performance numbers here are quite striking. The AME24 score of Qwen3-35B A22B increased from 70.1 to 85.1 over just 170 RL steps. That's a big jump.
It really is, and it demonstrates the profound power of well-designed reinforcement learning for truly refining a model's reasoning capabilities. GRPO, Generalized Policy Optimization, is a sophisticated algorithm that enables the AI to learn from its trial and error much more effectively. Instead of just taking the most obvious path, it's designed to explore a wider range of potential solutions and learn from those diverse experiences, making its problem-solving abilities much more robust and generalized. By carefully setting up tasks that are learnable but challenging, and by meticulously managing that trade-off between exploring novel solutions and exploiting known good ones, they achieve truly significant performance gains in complex mathematical and coding reasoning. That rapid jump in AIM-24 scores, which, is from a notoriously difficult high school math competition, vividly illustrates just how effective this targeted RL approach is at unlocking advanced reasoning.
Okay, now here's where it gets really interesting and I think truly innovative. Stage 3, thinking mode fusion. This involves integrating non-thinking capabilities into the thinking model via continual supervised fine-tuning. They design chat templates with explicit think and no-think flags, and even an empty thinking block for non-thinking mode to maintain internal format consistency. But the truly fascinating part is the thinking budget mechanism. The ability to handle intermediate cases, meaning incomplete thinking processes, apparently emerges naturally. You can literally manually halt the model's thinking process at a user-defined threshold and prompt it to generate a final response.
Yeah, this thinking budget mechanism is a genuinely clever technical solution. It's for controlling computational resources and balancing latency with performance in real-time applications. Instead of having to maintain entirely separate models, one for deep, reasoning-heavy tasks and another for quick, direct responses, they've ingeniously unified this capability within a single model. The natural emergence of handling intermediate cases means the model can deliver a response based on partially completed reasoning if a time limit or maybe a cost threshold is hit. That's incredibly useful for interactive systems where low latency is critical. It provides users with this fine-grained control over the depth of the AI's thought process for a given query. Allows them to optimize for speed, cost, or thoroughness depending on the specific application. It's a really pragmatic and powerful design choice.
That's a really practical innovation for real-world deployment, isn't it? Then stage 4, general RL, or general reinforcement learning. This stage aims for a broad enhancement of capabilities and stability across a truly diverse array of scenarios. And they leverage a highly sophisticated reward system for over 20 distinct tasks. These tasks cover everything from precise instruction following and strict format adherence to complex preference alignment, advanced agent abilities, and even specialized scenarios like retrieval augmented generation or RO.
This multifaceted reward system just speaks volumes about the complexity involved in aligning AI behavior with human preferences and desired outcomes across such a wide spectrum of tasks. They meticulously break down high-level goals into quantifiable feedback signals using 3 distinct reward types. First, there are rule-based rewards, used for objective correctness and strict adherence to instructions or formats. That's crucial for preventing what we often call reward hacking, where the AI finds loopholes. Second, they employ model-based rewards with a reference answer, which offers more flexibility for diverse tasks. And finally, model-based rewards without a reference answer, leveraging human preference data to train for subjective qualities like helpfulness, engagement, or creative output. This layered and sophisticated approach ensures the model is not only highly capable, but also behaves in a desirable, safe, and user-friendly manner across an incredibly wide array of real-world interactions.
They also focused heavily on strong to weak distillation for their lightweight models. Specifically, the dense models ranging from 0.6 billion to 14 billion parameters and their 30B A3B MOE model. The core purpose here is to optimize these smaller models by intelligently leveraging the deep knowledge and reasoning capabilities from much larger teacher models, like the Qwen3-32B or the flagship Qwen3-235B A22B. And this strategy significantly reduces computational costs and development effort for smaller models.
Absolutely. This is an incredibly smart and increasingly vital strategy for efficiency and, frankly, for democratizing access to powerful AI. Training the largest models is astronomically expensive, right? But once you have a powerful teacher model that has learned complex patterns and reasoning abilities, you can transfer its knowledge to smaller student models far more efficiently and at a fraction of the cost. They achieve this in 2 key phases. First, an off-policy distillation phase, which combines the teacher model's outputs from both its think and no-think modes. This helps the student model develop basic reasoning and critical mode switching skills. Then, in the on-policy distillation phase, the student model generates its own responses, and it's fine-tuned by aligning its internal logic, or logits, with the teacher models, minimizing what's called KL divergence.
And the results of this distillation are really compelling. Distillation achieves significantly better performance than direct reinforcement learning for the smaller models, and with only about 110 of the GPU hours. For instance, the Qwen3-8B on AME 24 saw distillation yield a score of 74.4 compared to RL 67.6, all while using just 1,800 GPU hours versus nearly 18,000 for RL. What's even more interesting is that it also improved exploration, as shown by better path at 64 scores for AMD UTGAR 25, unlike RL, which sometimes struggles there. So what does this all mean for you, the listener, especially those looking to deploy AI?
Yeah, this is a massive implication for widespread adoption and cost effectiveness. It means that smaller, more efficient models can still gain powerful reasoning and coding capabilities previously reserved for models orders of magnitude larger and more expensive. This distillation process is a key enabler for bringing truly advanced AI closer to edge devices, reducing deployment costs, and making high-performance AI accessible to a much wider range of developers, startups, and applications that simply don't have the budget or infrastructure for the largest models. It fundamentally lowers the barrier to entry for utilizing cutting-edge AI.
That's a truly significant practical implication, really democratizing access to powerful AI. Okay, let's dive even deeper into the performance now, looking at the rigorous benchmarks they conducted. For pre-training evaluations, they performed comprehensive benchmarking across 15 diverse benchmarks, covering general tasks, math and STEM problems, coding challenges, and multilingual capabilities. Their flagship pre-trained model, Qwen3-235B A22B base, showed remarkable dominance, consistently outperforming previously open-source, state-of-the-art dense and MOE models, and doing so with significantly fewer total or activated parameters.
Right? This is a powerful demonstration of the inherent power and cost-effectiveness of their MOE models, offering superior performance with a substantially reduced computational burden. To give you a concrete idea, the Qwen3-235B A22B base model, for instance, outperformed DeepSeek V3 base on 14 out of those 15 benchmarks. Despite having only about 13 of its total parameters and roughly 23 of its activated parameters. Furthermore, it even beat Llama 4 Maverick base, a model that boasts twice the parameters on most tasks. These specific ratios are not just numbers, they are powerful indicators of the architectural and training efficiency gains they've managed to achieve across the board.
And on the MOE efficiency specifically, these Qwen3 MOE-based models achieve comparable performance to their own Qwen3 dense-based models, but by using only 15 of the activated parameters. That's striking. They also consistently outperform Qwen 2.5 MOE-based models with less than half the activated parameters, and in some cases can even achieve comparable performance to Qwen 2.5 dense-based models with just 110 of the activated parameters. These are not small incremental improvements. These are truly leaps in efficiency.
They absolutely are not small improvements, no. These specific ratios are powerful, almost staggering, indicators of truly exceptional efficiency and engineering prowess. It signifies that their advancements in MOE architecture and their training strategies are delivering immense value, allows them to extract far more performance per activated parameter than previous generations. This is a critical step towards creating more sustainable, scalable, and ultimately more accessible large language models for a broader range of applications and users.
Definitely. Beyond their impressive MOE advancements, the Qwen3 dense models, like the Qwen332B base, also show significant performance improvement and resource reduction. For example, the Qwen332B base achieves comparable performance to larger Qwen 2.5 models, like the 72B base, but with half the parameters. Especially notable in STEM, coding, and reasoning tasks. It even significantly outperformed Llama 4 Scout base on all 15 benchmarks, with only 13 the parameters, although, fair enough, with twice the activated parameters in that specific comparison.
Yeah, and this confirms that the improvements are not confined solely to their MOE strategy. The underlying dense model architecture and the entire training process have also undergone substantial refinement. It's really a testament to the holistic advancements across the entire Qwen 3 family, making all their models more efficient and performant for their respective sizes. Offers a compelling choice for various deployment scenarios.
Okay, moving to the post-training evaluations, where the models are instruction-tuned. The assessments here were conducted on an even broader array of new, challenging benchmarks. These included general tasks via LiveBench, alignment tasks like IFEVL and ArenaHard, various math and text reasoning challenges such as Math 500 and AIM 2425, critical agent and coding benchmarks like LiveCodeBench V5 and Codeforce's ratings, and extensive multilingual tests. Their flagship, Qwen3-235BA22B, achieves state-of-the-art results among open-source models in both its thinking and non-thinking modes, even proving highly competitive with closed source leaders like OpenAI 1, Gemini 2.5 Pro, and GPT-4o.
Right, this is where we truly see the immense payoff of their sophisticated multi-stage training. It demonstrates incredibly robust capabilities across very different operational nodes. For instance, in its thinking mode, it consistently outperforms DeepSeek R1, even with fewer parameters, particularly in crucial areas like math, agentic tasks, and complex coding. And in its non-thinking mode, it exceeds the performance of models like DeepSeek V3, Llama 4 Maverick, and their own Qwen 2.572B Instruct. Remarkably, it even surpasses GPT-4o 2024-1120 in 18 out of 23 benchmarks. This shows that whether you need deep, deliberate reasoning or rapid, direct responses, the model consistently performs at an elite, cutting-edge level.
And it's not just the largest model that's making waves. The Qwen332B, their flagship dense model, is also a new state-of-the-art reasoning model at its size, outperforming QW-Q32B and competing strongly with OpenAI O3 Mini. Furthermore, even the lightweight models, from the Qwen330B-A3B down to the smallest dense ones, exhibit superior performance compared to other open-source models with similar or even larger parameter counts. This conclusively confirms the effectiveness of that strong-to-weak distillation approach we discussed earlier.
Yes, exactly. And this is a key implication for widespread adoption. By effectively transferring complex reasoning capabilities from their larger, more powerful models to smaller, more deployable ones, they are fundamentally lowering the barrier to entry for advanced AI. This enables these powerful capabilities to be utilized in more resource-constrained environments or for applications where latency, energy consumption, and cost are critical factors. It truly democratizes access to high-performance AI.
Absolutely. Let's maybe discuss some particularly insightful points from these extensive evaluations. Firstly, the effectiveness of their thinking budget. Figure 2 in their report clearly illustrates a direct correlation. Performance improvements across math, coding, and STEM domains consistently scale with an increased thinking budget, showing remarkably smooth and scalable gains. This is a very promising sign. However, what often isn't explicitly detailed in these papers is the precise computational cost increase for users when utilizing a larger thinking budget. Is it a linear increase in cost, or are there clever underlying optimization techniques beyond what's stated to manage that cost for external users? This feels like another one of those what papers don't talk about points.
That's an extremely practical and pertinent question, yeah. For anyone considering deploying these models in a real-world scenario, while the graph clearly demonstrates performance scales, the underlying computational cost for a user requesting a higher thinking budget is almost certainly not strictly linear. There are usually diminishing returns on performance for increasing compute. While optimizations might involve more efficient parallel processing of those internal thought steps, or maybe dynamic pruning of less promising reasoning paths, those specific details are typically proprietary, or just not fully disclosed in research. So for the end user, it generally means a trade-off. You get more thinking for potentially better results, but at an unquantified and likely significant increase in inference time and compute cost. It's a key area that definitely merits further practical benchmarking and transparency from the providers.
Right. Another powerful finding is the stark effectiveness and efficiency of their on-policy distillation. For instance, as you mentioned, distillation yielded significantly better performance than direct reinforcement learning for the Qwen3-8B on AMI 24, achieving 74.4 versus RL's 67.6. And critically, this was achieved with roughly 110 of the GPU hours 1800 versus nearly 18,000. Furthermore, it also improved exploration, as evidenced by better pass at 64 scores.
Yeah, this is a monumental technical efficiency win. It means they can develop and improve models much faster and with significantly fewer resources. It makes the iterative development cycle much quicker and less expensive. The fact that distillation also improved exploration, meaning the model became better at finding diverse, correct solutions, not just single correct ones, is a particularly powerful advantage over traditional RL, which can sometimes struggle with sufficiently exploring the solution space. This enables both faster development cycles and the creation of more capable, smaller models, all while being more resource efficient. Huge win.
The effects of thinking mode fusion and general RL are also very interesting. Stage 3, thinking mode fusion, showed initial mode switching ability, improving a metric called think follow to 88.7. It also enhanced general capabilities and instruction following in thinking mode, with notable gains on benchmarks like counterfeit QA plus 10.9 and length citral plus 8.0. Stage 4, general RL, further strengthened these capabilities, pushing think follow up to 98.9 for highly accurate mode switching. However, here's a fascinating and perhaps counterintuitive catch. For some of the most challenging tasks, like AIM 24 and Live Code Bench, performance in thinking mode actually decreased slightly after stages 3 and 4. This raises an important question. Why might generalizing the model lead to a slight decrease in specialized task performance? It really suggests a fundamental technical trade-off between broad versatility and peak performance on highly complex niche problems.
That's an absolutely classic and fundamental technical trade-off in AI development, isn't it? The delicate balance between generalization and specialization. When you continue to train a model on a broader and broader range of general tasks, even with advanced reinforcement learning, there's always an inherent risk of what some call catastrophic forgetting, or simply diluting its specialized expertise. The model learned to be broadly competent and adaptable across many diverse domains, which is incredibly valuable for general-purpose AI. However, that broad versatility might come at the subtle expense of absolute peak performance on the very hardest, most specialized tasks it was previously optimized for. It's a fundamental challenge in building truly intelligent and versatile agents. How do you maintain expert-level performance in highly niche areas while simultaneously excelling across a wide spectrum of general tasks? In this case, they likely opted for overall versatility and broad applicability, which makes sound strategic sense for a foundational model family, accepting perhaps a minor trade-off on the absolute bleeding edge of certain highly specialized benchmarks.
That makes sense. Another intriguing point is their long context ability evaluation. The Qwen 3 models clearly outperform Qwen 2.5 in non-thinking mode at long contexts, which is great for tasks that don't require deep reasoning. However, thinking mode performance slightly degrades when giving very long contexts. The hypothesis mentioned is that the model's own internal thinking content might interfere with information retrieval for non-reasoning tasks.
Yeah, this highlights a truly fascinating technical challenge. How to ensure the model's internal thinking processes don't become a hindrance for tasks that simply don't require it, especially when dealing with incredibly long contexts. For a straightforward retrieval task within a massive document, the model might inadvertently waste computational cycles thinking or generating internal reasoning steps. That additional internally generated content could potentially clutter its internal representation or even obscure the truly relevant information it needs to retrieve, leading to that slight performance degradation. It's about optimizing the internal decision-making of the model, making it smart enough to know when to engage its deeper reasoning capabilities for complex problems, and when to simply act as a fast, efficient information retriever for simpler tasks. This is a subtle yet critically important area for future improvements in agentic AI.
Definitely. Finally, their multilingual ability is incredibly impressive. The Qwen 3 series models achieve competitive performance across an astonishing 80 languages and dialects in the Bell benchmark, significantly outperforming their previous Qwen 2.5 series and showing comparable results to models like Gemma.
Right. This conclusively demonstrates the broad applicability and robust multilingual capabilities of the Qwen 3 series across diverse linguistic contexts. Expanding language support from 29 to 119 languages is a massive undertaking, demands meticulous data curation, sophisticated training strategies, significant computational resources. Their success here means these models can truly be deployed globally, serving a much wider user base effectively and breaking down language barriers in AI applications worldwide. It's a huge step towards truly inclusive global AI.
All these remarkable technical advancements naturally lead us to the practical aspect of deployment, and they've clearly put considerable effort into making Qwen3-Coder accessible to developers. They've open-sourced a command line interface tool called Qwen, which is forked from Gemini code but with customized prompts and function calling protocols. And importantly, it supports the widely used OpenAI SDK. You can also integrate Qwen3-Coder with Claude Code either via a proxy API or through router customization using Claude Code Router and Claude Code Config NPM packages. There's even configuration details for using Qwen3-Coder 480B, a 35B instruct with Klein via an OpenAI compatible API, plus direct API access available through Alibaba Cloud Model Studio, complete with Python examples. Looks like they've covered a lot of bases.
Yeah, this demonstrates a very clear and commendable commitment to making the model accessible to developers through multiple varied integration points. Providing support for popular tools and SDKs like OpenAI's and Claude Code, alongside direct API access through their cloud platform, significantly lowers the barrier to entry for developers who are keen to experiment with or integrate Qwen3-Coder into their own applications. It's a very smart move for fostering wider adoption and encouraging community engagement and innovation around their models.
Absolutely. But while they provide comprehensive installation steps and API access details, what often isn't fully discussed in these papers are those crucial practical aspects. Things like managing API keys, handling potential rate limits, or the precise real-world operational costs for smaller developers or companies using these tools outside of Alibaba Cloud's highly optimized ecosystem. These are critical details for anyone looking to move beyond experimentation and into production. Another what the papers don't say moment.
You're absolutely right. The technical report, by its nature, focuses on capability and integration methods, but the operational realities are often far more complex and can be a significant hurdle. API key management, ensuring robust security for those keys, understanding and navigating dynamic pricing models, preparing for potential rate limits, which can significantly impact application responsiveness and scalability, are all crucial considerations for developers. These details, while not directly related to the model's architecture or training, are absolutely vital for practical, real-world deployment and represent the everyday challenges that developers face when working with large language models in a production setting. It's definitely a space where more transparency from model providers would be hugely beneficial.
Agreed. Looking to the future, they're still actively working to significantly improve the coding agent's performance, aiming for it to take on even more complex and tedious software engineering tasks, with the ultimate goal of dramatically freeing human productivity. They also plan to release more model sizes to balance strong performance with further reduced deployment costs. And most provocatively, perhaps, they're actively exploring whether the coding agent can achieve true self-improvement.
Yeah, and if we connect this to the bigger picture, that pursuit of self-improvement in AI agents is truly the ultimate frontier. This represents a monumental leap beyond human-supervised learning, moving towards autonomous capability growth. If achieved, this could fundamentally change how software is developed. With agents iteratively refining their own code, debugging their own errors, even autonomously formulating and executing new problem-solving strategies. It's a grand, almost sci-fi vision that would represent a paradigm shift in AI autonomy.
It definitely feels like sci-fi sometimes. And what often isn't fully elaborated upon in the research papers, however, are the precise technical hurdles or the theoretical breakthroughs that might be needed for true self-improvement in a coding agent. Is it simply a matter of feeding it more data and throwing more compute at it? Or are entirely new algorithmic paradigms, perhaps even some fundamental theoretical understanding, required to enable an AI to genuinely learn, identify its own weaknesses, and improve its core capabilities without explicit human intervention? What do you think?
That's precisely the multi-billion-dollar question at the cutting edge of AI research, isn't it? While more data and compute can certainly lead to incredibly impressive emergent capabilities and performance scaling, true, robust self-improvement likely requires fundamental breakthroughs. Areas like meta-learning, learning how to learn advanced abstract reasoning, maybe even dynamic model architecture adaptation. It's not just about accumulating more knowledge, it's about developing the capacity for genuine self-reflection, introspection, and the ability to autonomously formulate and execute novel learning strategies. This moves beyond merely scaling existing methods and deeply into the realm of entirely new algorithmic paradigms that are still subjects of intense active research and theoretical exploration. It's where, yeah, the science fiction meets the bleeding edge of computer science.
It's going to be fascinating to watch. They also plan to continue scaling pre-training with even higher quality and more diverse data, and to keep improving model architecture and training methods for effective compression and scaling to even more extremely long contexts. And critically, they plan to significantly increase computational resources dedicated to reinforcement learning, with a particular emphasis on agent-based RL systems, learning from environmental feedback for complex tasks that require inference timescaling.
Yeah, this outlines a truly comprehensive and ambitious roadmap, leverages their current strengths while boldly pushing into challenging new areas. The explicit focus on inference time scaling for agent-based RL is critical because real-world agent interactions, especially in complex domains like software engineering, are highly dynamic. They require real-time decision-making and adaptation based on immediate environmental feedback. It indicates a clear understanding of the practical demands for truly autonomous and capable AI agents that can operate effectively in the wild.
So wrapping up, today we've taken an exhaustive deep dive into the Qwen3 series. From the truly impressive agentic capabilities of Qwen3-Coder to the nuanced architectural choices, the meticulous multi-stage training processes, and the remarkable performance across diverse and challenging benchmarks, we've seen firsthand how strategic scaling of data, context, and reinforcement learning, coupled with efficient mixture of experts' designs and clever distillation techniques, are propelling these AI models to unprecedented levels of coding and reasoning prowess.
Absolutely. This deep dive has truly highlighted how relentless technical innovation in model architecture and sophisticated training strategies, combined with incredibly meticulous evaluation, is not just bridging, but in many cases, outright closing the gap between open source and proprietary models. The profound focus on agentic capabilities, combined with the efficient deployment of lightweight models, means these advancements could very soon fundamentally reshape how software is developed, maintained, and maybe even conceived.
So after unpacking all of this groundbreaking work, here's a thought for you to mull over as you go about your day. As these AI coding agents become increasingly capable of tackling complex, long-horizon tasks and even begin to genuinely learn to self-improve, how might the role of the human developer fundamentally evolve? What entirely new frontiers in software creation become possible when our primary interface with code shifts to interacting with an increasingly intelligent, autonomous, and truly agentic AI?